Welcome to The Explainer. Think about the world around you. Electric cars, the renewable energy grid, all the electronics we rely on. They're getting faster and more complex every single day. And that creates a pretty massive challenge for the people who have to design and test them. So let's get into it.
So here's the fundamental question. How do you even begin to test a system where the most critical things happen in a flash? I mean, literally, in billions of a second. You can't just build a new prototype every time you want to try something. That would be insanely expensive, not to mention potentially dangerous. The answer? Well, it lies in simulation.
For a long time, the industry standard for this has been hardware in the loop, or HIL. The idea is pretty cool. You take the brain of a system, so the physical controller, and you plug it into a supercomputer that pretends to be everything else. You know, the EV motor, the solar farm, the whole shebang. It's a fantastic tool, but, and this is a big but, for today's super fast electronics, it's starting to hit a wall.
Here's the kicker. To test something that switches on and off millions of times a second, your simulation has to do all its math for one tiny slice of time before the next slice of time happens in the real world. The simulation literally has to be faster than reality. And as our electronics get faster, those time slices or time steps have to get smaller and smaller and smaller. Just how small are we talking? Well, for some of the latest power converters, research shows that the simulation has just 12.5 nanoseconds to get its work done. That's 12.5 billionths of a second, an impossibly short amount of time. And this single tiny number creates a massive problem for the very heart of the simulation, the program that does all the math, called the solver.
And this brings us right to the core of the issue, what we're calling the solver's dilemma. It's a battle, really, a classic engineering showdown between two different ways of running the numbers. It's a trade-off between going incredibly fast and, well, not crash.
Okay, let's break this down. On one side, you've got your explicit solvers. Think of them as sprinters. They are blazing fast, they don't use a lot of computer power, and they're perfect for hitting that nanosecond deadline. The problem? They can be unstable. They can fly off the rails and give you complete garbage for an answer. On the other side, you've got the marathoners, the implicit solvers. These guys are rock solid. They are guaranteed to be stable and finish the race correctly. But they are computationally heavy, they eat up memory, and they are way too slow for real time.
So what do you do? How on earth do you get the raw speed of that sprinter, but with the rock-solid stability of the marathoner? Well, it turns out the answer isn't one single thing, but a whole toolkit of really clever engineering tricks.
Researchers have come up with this whole toolkit of ingenious methods to just completely sidestep the dilemma. They combine the best of both approaches using some clever math and a really deep understanding of how the computer hardware actually works.
We're going to dive into 3 of these brilliant strategies. First, partition and conquer. Then, the hybrid approach. And finally, the leapfrog technique. All right, trick number 1. This is a classic divide and conquer approach. It's called topology-aware matrix partitioning, or TAMP. The idea is simple. Instead of trying to calculate the entire ridiculously complex circuit all at once, the system is smart. It breaks it down into smaller, more manageable chunks based on how the circuit is actually laid out. And the benefit, it is just enormous. By splitting the problem up, you don't have to store these giant tables of data for every single possible thing that could happen. The result is that a TAMP method can use that stable marathoner approach, but with just 1/15 of the memory. That is a massive, game-changing saving that lets you simulate way bigger systems on the same hardware. Okay, on to our next trick, the hybrid approach. This one's a little more surgical. The implicit-explicit, or IMEX solver, is smart. It recognizes that not all parts of a circuit are equally hard to figure out, so it uses the fast sprinter method for the really tricky parts and the safe marathoner method for everything else. So here's how it splits up the work. It looks at the really complex, nonlinear parts of the circuit, you know, like weird magnetic fields, and it solves those with the fast, explicit method to avoid getting bogged down. Then, for all the standard, more predictable parts, it switches over to the implicit method to guarantee everything stays stable. It's the best of both worlds, applied intelligently inside the very same problem. Our final trick today might just be the cleverest of them all. The semi-implicit parallel leapfrog, or SPL solver. Well, it kind of plays with time itself. See, instead of just calculating what's happening at the start and the end of that tiny 12.5 nanosecond step, it actually sneaks in another calculation right in the middle.
It literally leapfrogs through time. So it might calculate the voltage on a capacitor at the full step, but then it calculates the current in an inductor at the half step. By alternating back and forth like this, it captures this extra little data point, a half-step sample, that pretty much every other method misses completely. And the payoff is huge. You effectively double the sampling rate of the simulation. That means you're getting twice the information, twice the accuracy, without adding a single extra piece of hardware or slowing anything down. It's a purely mathematical way to get a much, much better picture of what's going on. Okay, so these tricks are amazing. They let engineers simulate a perfect circuit inside a perfect lab. But what about the real world? You know, the one that's messy and unpredictable and constantly changing? Well, that's where the next level of simulation comes in. Welcome to X in the Loop, or XIL simulation. The X here is a variable. It stands for, well, almost anything. It represents all the external, dynamic, and sometimes just random stuff from the environment that gets fed into the simulation to make it way more realistic. So, what kind of X factors are we talking about here? Well, for a wireless charger on a train, X could be the exact position of the charging coil as the train vibrates. For a wave energy generator out in the ocean, it could be the actual sea state. For any device, it could be the room temperature, the health of the battery, or noise coming from the power grid. XIL lets you test how a system will behave not just in theory, but in messy, chaotic reality. So, we've gone from testing a perfect circuit to testing a circuit in a messy world. But what if we could use these hyper-accurate simulation tools not just for testing something before it's built, but for monitoring a system that's already out there running right now?
This is the incredible idea behind the real-time digital mapped method. You're essentially creating a live digital twin. You run one of these ultra-fast, ultra-accurate simulations in parallel with the real physical machine. You feed it the exact same control signals that the real device is getting, and it creates this perfect digital mirror, a sensorless window that lets you see everything happening inside the machine live.
And the advantages over the old way of doing things? They are just staggering. Instead of plastering a machine with tons of expensive physical sensors and complex wiring just to get a few little data points, the RTDM method is completely sensorless. It just listens to the controller's signals, and in return, it gives you full digital visibility into every single part of the system. It's cheaper, it's non-invasive, it just works.
When you step back, the journey here is just incredible. Thanks to all these advanced techniques, engineers have gone from simply testing a blueprint on a computer to creating a live, high-fidelity digital window into a complex machine while it's actually operating out in the real world.
This massive leap in what's possible leaves us with one fascinating final thought. If we now have the tools to create a perfect, live, digital twin of any machine we can build, what are we going to be able to simulate next? The possibilities are truly staggering. Thanks for joining us on The Explainer.